Okay. How are you?
Waalaikumsalam.
How are you? Fine.
Thanks, Doctor. Fine,
Fine,
fine.
Doctor. Alhamdulillah.
Good, good, good. So you all busy with what we call it test weeks, right? So you have all tests in this week and also next week, right? Are you worried or not? No, right?
Doctor, we are ready, Doctor.
Yes, you are ready with a lot of strategy, right? Some of you, the strategy is when you just got the question. Yep, the first thing that we need to do is post that question into our group. And some of your friends doing some mistake. Oh, he post that question to the class group, right? And then he just wow, oh I need to delete that. Okay. But then the lecturer just realized, wow, okay, anyway. Okay, can I start the class now?
Yes, Doctor.
Okay, good. All right. Let me recap back what we have learned so far. So we have learned first order, right? Okay, first order. So the first order is the enemies, right? For the skywalker, right? Okay, no. And then we also have learn about second order, right? Okay, so the first order we can get this kind of graph. Okay, wait, I need to accept all first. Right, and then for the second order, we also have learned this kind of graph. Okay, right. So the second order we have three graph. It depending on your damping ratio, right? So whether your damping ratio less than one, as mean what we call it equal to one, equal to zero, less than one, more than zero, and so on. Okay, and the ratio equal to one. So here we got this kind of graph. Okay, and we also have learned about the basic control system that we have uh, three parameter, right, for the control system here, plus and minus here. So now we have the gain here. This one we call it controller, right? And then we have the G, sometimes we call it gain. So this one we call it a process, right? A process that's mean you cannot change, right? Okay. For example, when you buy the mouse, all right, for example, so this is the process, right? So what are you going to do? You apply some K in this mouse, for example, right? Right. If you want to do some improvement about the speed, for example, and so on, right, etc. And then you can have a sensor, right? So feedback, we call it H, right? And then you put it here. Then this is your input, right? You want to test it, right? Your desired input, and then you will got the output is Y. Okay, so this is the desired, or we call it is reference. Okay, so for example, like our system is air conditioning, right? So you set it is 20 degree. So you make sure that you can get it here is 20 degree, right? But how long that you can get the 20 degree? How fast is it? By looking at the time constant, right? The settling time. Okay, so that's what we have learned before. By looking the graph, so we know, oh, this our system, we can get the 20 degree at 4 seconds. Okay, for example, right? So on beside that, on this graph, we also look at last value. We call it is steady state error, ESS, right? Steady state error. So by looking at the graph, we know, oh, this is the steady state error that equal, right? The most important thing, right? The first order also have the steady state error. Okay, and in this topic, what we're going to look at, what is the value of the steady state error. Okay, it is depending on the input, right? For example, we just learn about the step input, right? Step input. Okay, we also have a ramp input, all right? And we also have a parabolic input, right? So when we apply the step input, what is steady state error? When we apply the ramp input, what is the value for steady state error? Okay, so when we apply the parabolic input, what is the value of parabolic input? Okay, and later on we will look the what we call it, stability of our system, right? Stability, that's mean maybe your, when you look at the graph, your system is look stable, right? It looks stable, it can achieve. Or maybe later on your system will go like this. Oh, it's not stable anymore, right? Okay, right? So we will look into that, right? We can know that whether our system, right? Our system, when we apply K and so on, is stable or not. So today, what we're going to achieve is steady state error. Okay, what is the value? And also to check whether our system is stable or not. Okay, this is two objectives that we're going to learn in this class for today. Okay, now is it clear for only the introduction? All right, clear? Clear? Hmm.
Boleh Doktor?
Okay, good. Right. I already give it to you the notes that I already updated with the we call it a lectures note, right? Because the note that you download from the e-learning is a student note, I think. Okay. Now we will look about the effectiveness of feedback system. It means the steady state error. Okay. So I just draw it again. You got it. A general closed loop system here. This is G, and you got it a sensor, so this is H, and you got it here, plus and minus. Okay, now your input, let's say this is U, right, in Laplace, right, US, and this one is output Y. Okay, now when you got a feedback here, right, then we got it is this one, we got it is error, SESS, steady state error here. Okay, how much the steady state error and so on. So in order to calculate the steady state error, so you can do steady state error here. Okay, ES or E, that's mean error. Okay, so US minus H S Y S. Okay, this one H S Y S here. Okay, so steady state error U minus H Y. Okay, now we got it. All right. Then now when you try to simplify this one, K you time G, right? Then that's why you can we got it is YS. Okay. So now we can do like this one, US minus HS here. You time with K G here. Okay. And then when you follow at that one, you will got it is ESS equal to 1 over 1 plus KGH. Okay. And then you multiply with your U. Alright. So this is the formula, right, to find the steady state error. Okay. So how to make it simple word? So we just use final value theorem, FVT, right, in order to get the solution for this steady state error. So you need to put the limit, right? The limit. Okay. So T, right, in term of time domain, and then you need to time with function T here, or in term of Laplace, you can put it is S going to 0, and then you need to S, then ESS here, okay? then you got it is limit s going to 0 to 1 1 plus k, right? So G, this is has S and S has, and you now have a US here. Okay, so this is the statistical error here. Okay, right? But it's okay. You don't need to remember all this one. All right. So what you need to remember the concept is, okay. So now you got it is ESS here. Okay, 1 divided 1 plus KGH. Okay. So need this one you need to time by U. Alright. Now we know this one is the formula for the statistical error. So let's say we apply the step input here, right? The step input. So we got a lot of input here. It's the step input, impulse, and sinusoidal, and also ramp input. Okay. So let's we apply the step input first for this formula. Okay. Right. So far so good. Okay. Boleh eh? Eh? Clear eh? So this is only the introduction. Okay, good, good. So let me apply this one. Yes, S and limit S going to 0, and then you S you time with S here lah. And then you can get it limit going to 0 1 plus if you can make it forward, right? You okay, it will be good. Okay. Now then you time with your US. Okay, U for the step input is 1 over S. So now you time it with 1 over S here. Then we got it is limit, okay, S going to 0, 1 over 1 plus KGH here. Okay, let's say I don't want to write as okay. So do I cancel out? Okay, you got it this one. Right? And then let's say this one limit s going to 0 1 over 1 plus kp. Okay, we put a kp, it represent the kgh here. So you got it is kp limit s going to 0. Okay, let's redo this one. ss equal to 1 over 1 plus kp. Okay, the limit we gone, and then where you got it kp, limit s going to 0 is equal to kgh here. Okay, right? So when you want to solve the limit, so you can put it is kgh, then you will apply s equal to 0 here. Okay, all right. So when you apply the step input, the steady state error will be this formula. Okay, the steady state error will be this formula. Okay, so you can find your steady state error, what we call it, directly, right? You don't need to draw the graph. You don't need to see the what we call it, yeah, I mean the graph and the time and so on and so on. You just need to apply this formula, it depending on what the input that you have. Okay, that is the first input, step input. Okay, so far do you have any question about this one? Yeah. Okay, all right, no question? No. Okay, good. So now let's say you apply the RAM input, right? So RAM input, the input now will be different. We just focus only a certain input, okay? So now what you have here is ESS equal to limit S going to 0, and then SESS, okay? Then you got it is limit S going to 0. So this one is US, okay? S over 1 plus KGH here. And then USS for the ramp input is equal to 1 squared. Okay, so 1 over S squared here. Okay, now here we got it is limit S going to 0. So 1 over S1 plus KGH here. Okay, this one, right? Okay, so let's take a lim SCO 1 over, let's take another parameter we name is KV. Okay, KV or KP, KV. Alright, and then you got it is steady state error equal to 1 over KV, where your KV is equal to S plus S KGH here. Okay. Limit S going to 0, S plus S KGH here. Okay, this one. Alright, and then you want to cancel out the limit. We can say that as KGH, so S equal to 0. So because the S, this KGH here, the value will be more bigger than S here, right? More bigger than coefficient here. So we can say that K SGH equal to 0. Okay, so this is the KV. Alright. Okay. So when you apply the right input here, you will see that this is the formula that you're going to use for the steady state error, 1 over KV. Okay, so KV, what it means is the velocity error constant. Okay, that is the name that given it. Okay, so far okay. Do you have any question? Apa yang tak faham? Good. Hello. Yuhu.
Okay, sir. Everything okay?
Everything okay? Good, Lalita. Okay. Alright. So this one. Then another example when you apply parabolic input. So parabolic input, I'm not going to derive it. Okay. So parabolic input, when you apply it, now you will got it. Parabolic, that means U equal to 1 over S cubed. Okay. Then you will got it is steady state error is 1 over Ka. Okay. Ka is acceleration. Alright. So Ka, you will got it is limit S going to 0. Okay. S squared plus S squared KGH here. And then in order to uh, eliminate the limit, so S equal to 0 here. And we assume that KGH here is more bigger than this one, so we left is here. Okay, equal to 0. So this is the K. Right? So when you have the parabolic input, you also can find the steady state error by using this formula. Right? Okay, so let me simplify it again. Okay, so for the step input, right, then this one, ESS equal to 1 over 1 plus KP. Alright, where is your KP equal to KGH as equal to 0. Okay, this one. And then when you apply the ramp input, now you got it ESS equal to 1 over KV. So where is your KV, right? KV, okay, KV. Where is your KV equal to S KGH as going to 0. Okay. Am right? Okay, good. And then you apply the parabolic. Now you got it is ESS 1 over KA. Now KA is equal to S squared. KGH is equal to 0. Okay. Alright. So this is the three formula and three input, right? So we only focus on this input. Don't ask me another input, right? Okay. And this table is the guideline, alright? Is the guideline, right? The guideline that means if you found that your system is belong to the class 0, so when you apply the step input to your system, that means you will find that they will have a steady state error, right, for the class 0, okay, 1/1 plus kp. And then when you apply the right input for your system that belong to the class 0, you will got it infinity. Okay, your steady state error is infinity. That means your system is not stable, right? Okay, and parabolic, when you apply, the system is also not stable infinity. That is depending on the class, right? But this one is only the guideline. Okay, so how to find the class? So we have learned this one before. So by looking at the KGH, all right, and we need to look at the coefficient here for denominator. So this one is denominator. So and by looking the L, all right. So L, that means the class, right? Highest order of S. Okay. So let's look example 3.1 to make it clear. Right? You can remember the guideline or you don't need to remember. It's okay. Right? Okay. So this is the concept 3.1. So you got it is GH here is equal to 10 S plus 20. Right. So our objective is calculate the displacement error KP. Yeah, you say the KP. Okay. And steady state error. Okay, let's say we want to calculate the steady state error for three input, step, ramp, and also parabolic. Okay, what is the steady state error? Okay. Now, let's say we apply the step input to this system. Okay, step. When you apply the step input, that means the steady state error for the step input 1/1 plus Kp here. Okay, and then for Kp, how to find it is Kgh UH equal to 0. Okay, so let's find steady state error for this one first. So Kp is equal to Kgh. So this one Kgh, so K is 1 lah. Okay, where is 1. And then GH is 10 divided with S plus 20. And you put it is S equal to 0. Then you record it is S equal to 0 here, 0. So 10 divided with 20 is Kp equal to 0.5. Okay, alright. So steady state error is equal to 1 plus 0.5 here. Then you got it 0.76 here. Okay, so that's why I told you when you are given the transfer function, okay, right, KGH here, right, we just want to take the K, G, and H, all right, okay. So by knowing the KGH, so we can get the value for the steady state error. That is why when we apply the step input, okay. Right. Do you understand about it? Okay. Any question? Any question? Do you have
No.
any question? No? Okay. Clear, eh? Tengah je. Clear? Is it?
Yes, clear, Doctor.
Okay. Good. 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 I thought that I just shot sendiri. Okay. This one is your system, right? K, G, and H, the closed loop system. So now when you apply step, so you can get your steady state error ESS equal to 0.67. Okay. Now let's look when we apply the ramp, ramp input. So we know the steady state error for ramp input is 1/kV, where your kV is equal to what is it? S KGH and S equal to 0. Alright. So now S you time with kgh now is 10s plus 20, 10s plus 20, then you apply equal to 0. Now you got it is, yep, S equal to 0 here. So of course you will got it 0 here, right? 0 here. And how to find the steady state error? 1 divided with 0, 1 divided with kb. So of course you will got it infinity. So that means your system is not suitable to apply the RAM input. If you apply the RAM input, that means you will got it is infinity. The steady state error. That means you will write the graph, right? For example, maybe this one, the second order system, the graph will be go up. Okay, that's it. Okay. Can you understand about it? The concept? Okay, boleh?
Yes, sir.
Boleh. Alright. So now, when we apply the parabolic also, you will got it is as equal to infinity also. You can try it, right? You got it infinity. Okay. Right. Yeah. Yeah.
We need to test every input kah?
It is depending on your application lah. That means if you want to only test the step input, yep, you just test for the step input. Right. So by having tested at the different input, that means you can look your performance of the system, right? That means, oh, my system is robust, right? Let's say like that lah. Okay.
Sir.
Okay.
Yep.
So basically, if you want to determine the steady state error,
Yeah.
Since S approaches to 0, so just put S as 0, right? Like in most cases.
Yes. Correct.
All right.
Okay.
Thank you.
Right. This is one way, right? Okay. So let's look the class for this system, the class, right? Right. So how to look the class? 10 divided with S power of 0, S plus 20, right? Okay. So that means your class now is L equal to 0. So that means your system, this one, is class equal to 0. So that means you just need to look at this guideline table. Right. When the class equal to 0, you will be sure your step input will have certain value, but the rank input will have been infinity, but the parabolic input will also be infinity. Okay. Right. So you can depending on this class, or you can derive the equation is again, right? So when I derive it, you look at, oh, RAM, infinity, right? Parabolic, yeah, of course you will got it infinity. Okay, because the parabolic is only S squared kgh. So when you apply equal to 0, of course you will got it, the Ka will be equal to 0. So 1 divide with Ka, so of course you will got it infinity here. Okay, clear? Okay, no doctor, LCT, what is it? Not clear? Is it clear, guys? Do you have any question? Clear, doctor. Okay. Oh, no, that means don't have any question. Okay, that's it. All right. And then we will look another example. I think it is quite simple to understand about it. It is quite simple to understand. All right. Find the error constant. So that means the error is depending on step input or right input and parabolic input. Okay. Error constant, that means if the step input, we call it as the displacement error constant, Kp. And for the Kb, we call it velocity, and Ka, we call it the acceleration. Okay. All right. And this one is very simple. So you just need to know about the K, G, and H. So now H is equal to 1. Okay. So I already showed to you K, G, and H here. Then you got it this one. And then you apply the what you call it, step input, right? Step input Kp here. So this one is the Kgh, so S equal to 0 here. Okay. and you got it is infinity. Okay. You also can look at first. Oh, this system, right? This system is belong to which class? Okay, L equal to 2. Okay, that's mean class number 2 here. So whatever when you apply the state input, of course the state error you will got it 0. Okay. So when you apply the right input, yep, you will got also the 0. Okay, right? That's mean the steady state error will be 0. Wow, it's good. And when you put it parabolic, yeah, you will got it is 1 over Ka. So that's mean the steady state error is not 0 anymore. Right. So this means that your system is quite stable lah. Right. It's stable, right? Right. That's mean like I said, right? Like I said, this one, okay, I try to make you understand the concept. Okay, so when you got it, this one, okay, never mind. Let me go to this one. Okay, so based on the result, we got it Kp equal to infinity, so steady state error equal to 0. So this one is for the step input. All right. Number 2 for the RAM input. RAM input, now you got it Kb equal to infinity and steady state error equal to 0. Okay, and then for the parabolic input, then you got it is Ka equal to 0.25, and then you got it steady state error 1 over 0.25 equal to 4. So what is mean? This one is mean like let's say this is your step input. Step input will have okay, like this one, right? Okay, so this one is 1, right? Okay, for example, you put in 1. So what happened to the output when until you got it the steady state error equal to 1? Okay, this will be the output. Yeah, that's mean this is your steady state error, which is equal to 0. Okay. Yep. Okay. Clear? Yeah. So that means your system is stable lah. It's very good. Okay. Right? Okay. So the what we call it parabolic is different graph. It will be sine graph and so on. Okay. Right. For the RAM input, it is like we got it here. Okay. Then your output will be maybe okay, like that lah. Okay, so where your steady state error is equal to 0. Okay, right? Now it's clear. That one just now message. Okay, clear? Do you have any question? No? Ada apa-apa soalan? Clear? Alright. Okay, sir. No question. Good. Alright. So I can proceed. This one. What is it? Okay. The last example, I think, also same. This one, the KGH. Alright. So you can find the first class. Okay, class 0. That means you will only have the steady state error at the step input. For the step input. For the RAM input, you will have the steady state error infinity. For the parabolic input, you will have the error infinity also. So to prove that, you can find the Kp here. Yep, it is the steady state error. Only the 0.04 is a small steady state error, right? Cool. And then for the parabolic RAM input, infinity. Your term is not good for the RAM input, right? And then for the steady state error, for the parabolic, you will also got what we call it infinity also. Okay. All right. So that is how we can determine our steady state error. So today we have achieved how to find the steady state error. Okay. The part 1 has been achieved. Okay, delivered faham right? Part 1, steady state error. Okay, now we going to look whether our system is stable or not. By looking the steady state error, we can know that our system is stable, but how long it will be stable? That is our question. Okay. Right. Everybody good? Can we move to the next chapter? All BLL have left meeting. Can we move to the next chapter, guys?
Yes, yes.
Okay, doctor.
Okay. Alright. Okay, Navita, good. So, in this 3.6 is effect of time constant. This one is only for the first order. So, the last semester I teach. This one is just make some revision or some understanding about the first order. This time I teach the last semester lah, right? Because on that time the question is about the first order that you need to derive into detail. That's why I do some revision on that. Okay, now we going to the chapter 4. We got a 3 chapter more for this subject. So we going to look the stability. Okay, after this chapter it will be quite easiest, right? And it will be quite easiest, and it will be quite interesting because it will involve a lot of mathematical calculation there. Okay, ready? So that's it. Stability of the control system. Like I said it before, we have knowing the graph of our system, okay, second order or first order, right? And then we also have determined the steady state error. Done. And then now we want to know whether our system is stable or not. So there is one method to know that. Okay, so let's look the concept of stability first. So stability, that's mean when you apply input, right? For example, in past step, and maybe this is your input. You will got the output will be a same like maybe input and so on, right? So the stable system, that's mean your output here is still in boundary. So that's why we call it is bounded output. Bounded output, that's mean like this one. Maybe you got it. Okay, this is your system. This is the output, right? So is when you take it only the boundary, all right? This is the boundary, right? So this one we call it a bounded output. That means your output still in this boundary. So we can say that, yeah, initialize, your system is still stable, right? Okay, so how if you got this system, okay, yeah. So when we say that, oh, this one is still in boundary, okay, right? So that means we can say that our system is quite stable, okay, right? But if you get it, your system is not in boundary. For example, is outside the boundary. So that means your system is not stable anymore. So we call it is unstable system. There are two words here we are going to focus. So whether your system is stable system, and also your system is unstable system. Because when you become a controller engineer, right, a control engineer, and then you want to improve something about the equipment, about the device, about the machine and so on, you want to apply some controller about it. So you need to test whether when you apply your controller into that system, you need to test, oh, okay, overall system will be stable or not. Okay, if not stable, it will be a big mistake about it. Okay, right? That's why we're going to check. Okay, right. And by default, example system that is stable or unstable, when we look at the positive root, make the system unstable. Okay, for example, this one, y over u is equal to 1s plus 1, right? So by looking the roots, right, the root s equal to s plus 1 equal to 0. So s equal to minus 1. Okay, all right. So when you look at the positive root, that means positive root this one lah. Okay, positive root. Okay, positive root, that means this one. That means you will look at your system will be stable. Yeah, okay, it will be in boundary. Okay, and this graph is s equal to minus 1. That means when you got it is negative root, right? Negative root will make your system unstable, right? So there is no boundary. Okay, this one is no boundary here. Okay, so let's look the stability of the control loop system. So this is the general question block diagram for closed loop system. You got a K, G, and H here, and then you will have the general equation KG 1 plus KGH, right? This one, okay. Block diagram manipulation. You got it. This one general equation here. And how to know your system is stable or not? By looking at this one, characteristic equation 1 plus KGH. Okay, so we have done this one before. We have learned about the word characteristic equation in the second order system. All right, so in the closed loop system, for to check whether the system is stable, you're just looking at 1 plus KGH. Okay, we call it a characteristic equation. Alright, so this one blah 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 blah, that means you can also get the coefficient for numerator, right? The top one and the denominator, blah 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 lah. Okay, and then when we want to plot our roots, right? So normally we plot it in binary and real axis. Okay, the response is bounded if the pole are negative. Okay, right? Bounded, that means stable. Stability of the system is determined by pole only. Okay, all right. Now, when you have this equation, right? For example, okay. All right. So you have this kind of question. Okay, you got it s plus 1, s plus 3, and then s plus 4, s plus 5. So this one, we call it pole. Okay, and this one we call it zeros. Okay, so this is important information. Okay, so based on this one, it says that stability of the system is determined by pole only. That means you just look at the pole only, right? The roots at the pole, right? So it can determine whether the system is stable or not. So there is one word that mentioned that all poles of the closed loop transfer function, right, must have a negative real value. Okay. So when the all pole have the all negative value, that means you can say that your system is stable. Okay. Okay. The system is stable if all poles are located on the left hand side of the imaginary axis. Okay, this is another word. Alright. Okay. We will look into that. Okay. This is only the theoretical. Okay, we will look into this. Okay. Alright. Now you got it your system. For example, QS equal to S3 plus 4S squared plus 6S plus 4. Okay. Then you need to find the roots first. Okay. For this one, then you can factorize this one equal to S plus 2, S plus 2 plus 2S plus 2 here. Okay. And then you can make it a 0 here. Then you can find the roots for number 1. Let's say S1 is equal to minus 2, and S2 and 3 here. Then you need to apply back the formula, right? I also forgot the formula. Minus b plus minus b squared minus 4ac divided with 2a. Okay, And then when you apply this one, you will got it is minus 1 plus minus j. Okay. Do you still remember this formula, right? Betul kan? Masih lagi ingat formula ni kan? In order to find the roots, right? That you cannot
Right.
Okay, good. So, how to draw this root in this one? So, when we want to look our system whether it's stable or not, one of the method by drawing at the two axes, we call it is imaginary. I and G imaginary, and this one real. Okay, so now you got it is minus 2. Minus 2, that's mean real lah. So this one real, right? This one imaginary. Okay, imaginary. Right. So minus 2, that's mean you got it is minus 1 here. This means minus 2. So your first root, look at it, this one. Look at it at this point. And then you got it minus 1 and plus j here. Imaginary, that's mean your j lah. Okay. So this is the second root, the root number 2. Then you got it is minus 1 also. This one and minus 1. Then you got it is third root. Okay. Alright. So by looking the location of the root, alright, that you put it in the imaginary and real as a plane, right? So let's go back to this one. The system is stable if all poles are located on the left hand side of imaginary axis. So this is your imaginary axis. So all poles located at the left, at the left, okay, at the left, right? So we can say that our system is stable or not. Right now, is stable or not? What do you think? Okay.
Stable.
Okay, good. Because all pole is located at the left, right? So we can say that our system is stable. Okay, our system is stable. Good. So done. However, if you only have a simple equation, right? If you only have only s power of 2, you can use this formula, right? Okay, I'm right. If you have the equation for maybe this one is s power of 4, can you use this formula? It's very difficult, right? Kan?
No.
Yeah, it's very difficult. So that's why on the next slide, it will show you there is one method. We call it root stability criterion. Okay, before that, so let's look this example a little bit. Okay. For the imaginary stable loop system shown below determines the stability of closed loop system. Given the Kp equal to 24. Okay, so when you have the 24 here, K, and this one is your G actually. Okay, then you have a H equal to 1. So in order to find the stability, you just need to find the characteristic equation 1 plus kgh. 1 plus kgh equal to 0. So when you find it, this one, and then you will find the equation here, and then from this one you can plot your from the equation you can find the roots. So this is root number 1 minus 4, and for root number 2 and 3, so you got it this one. Okay, 0.0. Oh, I already put it root 3. Okay, right. So root s2 and s3 here. Okay. Then when you plot it, you found that, yeah, one of the pole at the left imaginary, but another one at the right imaginary. So tell me, your system is stable or not? In this case, unstable, right?
Unstable.
So because there is roots that located at the left hand, at the left or imaginary axis, right? So one is located at here and one is located at here. So that means your system is not stable. Okay. Then how about this one? Stable or not? Don't know. Okay. If your roots is located at the imaginary axis, you can say that it's not stable. It's what we call it is marginally stable, right? Marginally stable. So that means your roots need to be less than imaginary axis, right? Yep, it is almost imaginary axis. So that means if your root is located this one, this one, this one, so we can say that yeah, stable. If your root lie on the imaginary axis, that means we cannot say whether it's stable. Okay, we say that our system is not stable. Okay, this is how you draw. But remember, if you only got it is a simple equation, right, for the power of 2. So let's look if you have a very complex order, right? Okay, so you cannot apply this formula anymore. So what you can do is you can use the root stability criteria. Okay, what is it? It's a root stability criterion. Its method determine the existent positive pole. Okay, blah 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 blah. Okay, this is how you going to use it. Okay, so this one we time with this one, minus with this one, time with this one. Okay, okay, never mind. I will show it. Okay, this one is the okay, the rule. This table is filled horizontally and vertically until remaining element are 0. Okay, I will show you. The characteristic equation hold all negative root if the sign of all element in the first column are the same. Okay, this is the very important. So, okay, all of negative roots if the sign is same. Okay, the number of positive root is equal to number of sign change. Okay, never mind. So we will look into this. Alright. Okay. So example 3.5. Okay. I will go back later about that definition. Okay. Okay. That's why I told you this topic will involving a lot of mathematical equation, right? Calculation. Okay. S Q plus 20s squared plus 40s plus 50. Okay. Yeah. 50. Okay. Alright. So how to get this equation? Remember from the characteristic equation. So I like CE control engineering. Alright. Now characteristic equation. 1 plus kgh equal to 0. Okay. How to get this one is based on your block diagram, general block diagram here, G and H here, and feedback here, plus minus. Remember, so this one, kg and H, but you need to put 1 plus kgh. Okay. How also to get 1 plus kgh here? So y over u equal to kg 1 plus kgh here. So this one. Okay. Alright. Clear? Okay. Clear. So now we want to apply the roots table or root criterion. Okay. So how to write it? So first look at the first one, right? The first order. So you got it is s power of 4, right? The highest order is s power of 4. Then you need to write s power of 3, s power of 2, s power of 1 until s power of 0. Okay? And then you make some table there. How to draw it? Okay, I make it larger. So s power of 4, s power of 3, s power of 2, s power of 1, and s power of 0. The same size, right? Okay, now you make this table. Okay, 1, 2, 3, 4. Okay, this is the table. So, and how to fill in this one? To fill in this one, so by looking at this one, okay. Look at the coefficient for this one. So for the s power of 1, the coefficient is equal to 1, right? So that's mean this one 1. And then after that, look at the next one. Langkau sikit. Right? Look at the next step. Right? S power 4, look at the S power 2. So that means the coefficient is 20. Right? After that, langkau, okay. So what we call it as skip. Okay, skip this one. Put it. Look at this one, 50. Okay, 50. Then after that, put a 0. Okay. Done? Clear? Clear? Boleh faham? Clear? Okay. And then
Clear.
for the S power of 3, look at this one, 5. So put it 5. And then after that, you 40. Okay. Then after that, of course, 0, 0 lah. Okay. Done. Right. Okay. So, how to find this one? To find this one? To find this one? Okay. It will be like this one. So, divided with 5. First one, this one. Divided with 5. So, that's why it divided with 5. So, 5 times 20. How to write it? 5 times 20. Okay. I hope you can see that, right? You can see at the slide, at the note also. Minus with 1 minus 40. 1 minus 40. Okay. Right. So, I will write it. How to write it? 5 times 20 minus with 1 minus 40 divided with 5. Now you got it is here equal to 12. Okay.
Doctor, 1 minus 40 ke 1 times 40?
Oh, sorry. Good, good. 1 times 40. Good, good. Thank you, thank you. Nasib baik ada orang teman. Okay, 1 times 40. Good, thank you. Alright. Now you got it. It's 12 here. So right now this table is become 12. Okay. Done. Right. Clear. Then how to find this value? Alright. So delete this one. Delete this one. Okay. It's starting from 5 also. Look at the first column. This one, the first column. So divided with 5. So 5 times 50. Okay. So 5 times 50 minus with 1 times 0. So cost 0. Okay. Right. Then you will got it what? 50 lah. So this one, you will got it 50. Right. Another one, divide by 5 also. Only first column, divide by 5. 5 times 0 minus 1 times 0. So you will got it is 0. Okay. We are done. Boleh eh? Okay. Yang ini faham? Okay. Okay, good. So, how to find this one? Alright. Okay. How to find this one? Divided with 12. Alright. Okay. Look at here. Put it here. Divided with 12. And then 12 times 40 minus with 5 times 50. So 12 times with 40 minus with 5 times 50. 5 times 50. Okay. Now we got it is here. Yeah, I need to delete it back. Okay, now you got it here is 19.2. Okay. Then 12 times 0, right? Minus 5 times 0, of course you got it 0 here. Okay, right? Another one is 0 lah, right? Okay. And then after that, divided with 19.2. 19.2 times 50 minus 12 minus, what is it? Minus 0, right? Okay. So this one, I think it should be 50, right? Okay. I'm right, betul tak? Alright. Betul eh?
Yes, sir.
19.2 times 50 minus with 12 times 0. So of course this one 0. This one you cancel out. So you got it 50. So this one, sorry guys, messy sikit. Okay, 50. Done. So we already got all the value for the first column. For the root table, right? For the root table, we call it root table. We just look at the first column. The first column, this one. Okay, right? Okay, done. We just want to get the first column. Okay, so and then after that, we look at the sign of this value. Okay, uh, you have another column here. Okay, look at 1. What is the sign value? Positive or negative? Positive, right?
Positive, Doctor. Yes.
Okay. 5. Positive, right?
Positive. Yes.
Positive also. Positive also. Positive also. Correct. Okay.
Yes.
So let's go back. The characteristic equation has all negative roots if all the sign element in the first column are the same. So the number of positive root is equal to the number of the sign chain. How to get it? Okay. Positive pole. Okay. Yep. The root criteria method determine the thing. Okay. It doesn't say that. Never mind. Okay. That's mean when you look at all the sign, right, for the first column, right, so there is no sign changes. There is no sign changes. That means you can say that your system is stable because no sign changes. Okay, no sign change on the first column. So you say that your system is stable. Boleh? Okay. Alright. So far, so good. Can you understand about it? We just look at the sign, positive, 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 positive. Yeah, you are positive COVID-19. Okay, you know. Alright, that means you can say that your system is stable. Okay. Alright. Do you have any question? If you got it, this one you got it negative. For example, this one negative. That means there is one sign changes positive to negative. That means your system is not stable. Okay, that is the method. Okay, in order to use the root criterion, just look at the first column. Alright, boleh? Okay, so why we use this roots criterion? Because we cannot solve as power of 4, right? So that's why we use the root criterion. Okay, ada apa-apa soalan? Do you clearly, right? Understand clearly?
Yes, Doctor.
Okay, good. So let's look example 3.6. Okay, 3.6 here. It show you the example to determine your system is stable or not. Okay, now you got it is here. So maybe I can okay. Okay, so this is the equation from the 1 plus kgh equal to 0. Then you got it is s power of 3, s power of 2, 2s plus 24 equal to 0. So how to make this table? S power of 3, s power of 2, s power of 1, s power of 0. And then what is this one? Is 1, 2, done, right? And then this one is 1 and 24. This one 0. Okay. Then when you do this one, you will got it is s power of 1 here is minus 22. Okay. Right. Then s power of 0 is 24. So the sign for this one is plus, plus, minus, plus. So that means there is one change in the plus. That means you can say that your system is unstable. So that's it, right? You don't need to draw the graph. You don't need to that means look at the graph and so on. So you just do the root table. Okay. Alright. So, or we can say that all elements don't have positive sign. Okay. Alright. Okay. Alright. Okay. This will be the last one. Good. Yeah. Example 3.5 here. Okay. Now you got it, the 1 plus kgh. So k here, right? G here, and h equal to 1. Then you find 1 plus k. You time with the g1 over s plus 3, s plus 10 equal to 0. Now you got it is when we try s2, 13 s2, s plus k equal to 0. Okay, so the question is determine the range of k. Okay, k equal to what? Okay, the range of k to ensure that the system is stable. Okay, this is our system, right? So 1 plus kgh here. So we can use the root table here. Okay, s power of 2, s power of 1, and s power of 0. Okay. Alright, so s power of 2, that's mean 1, right? Then you skip it, 30, okay, done, and then 0 here lah. Okay, and then 13 and k and 0 here. Alright, so this one for s1, sorry, divide with 13. Okay, 13 here, divide with 13. 13 times 30 minus with 1 times k here. So we got it is 390 minus k divided with 13. Okay, so this one we got it k divided with 13 here. And then 13 times 0 minus 1 times 0 divided with 13, you got it 0 here. Okay, done. Right. So to find this value, so divided with 390 divided k with 13. Alright, so 13 times 0, 0. Oh, sorry, this one times this one, so 13k divided with 13 times k minus with 13 times 0. So you got it, this one 0, this one cancel with this one, then you got it is k. Now you got it is k. Okay, alright, good. Okay, done. So this is the root table that we got it. So in order to know the range of the k at your system is stable or not, that means we got it all is positive sign, right? Positive sign, positive sign, positive sign. That means your system will be stable, right? So in order to get the positive sign, that means 390 minus k divided with 13 must equal to 0. Okay, then when you do that, you can get it 390 equal to k. So that means your k is equal to 390. Okay, right? So when your k equal to 390, that means we got it equal to 0. Okay, so that means your system is stable. That means when k equal to 390, this one you got it 0, right? So it means it's still unstable. Okay, right? So for the varying of k is k less than 390 and can be more than 0. Okay, right? Can you get it?
Yes, sir.
Okay, so if I say that k equal to 0, yeah, k equal to 0, we also can accept it. So, yeah, this one. More and equal. Because k equal to 0, we can accept it, right? So, 319 minus 0 divided with 13, right? We still got it positive, right? I'm right, betul? Okay? I am right?
Yes.
Okay, good. Oh, no. It cannot be 0, right? Sorry. Why? Why it cannot be 0? This one, right? Okay. When you put it is k equal to 0, that means the coefficient for this one, it is like s plus 0. So you will have one roots, right? At the imaginary axis. Okay. Can you get it? Boleh
Okay.
nampak? Okay.
Ya, boleh.
So that's why it need to be more than 0. So that your roots, it will be at the left. Okay. It will be at the left, right? Okay. So that's why you cannot put it is more than 0. And then it need to be less than 390 because we don't want to get equal to 0 here. Actually, we don't want to get it because if we put it 0, that means your roots will be lie at the imaginary axis, IMG here. Okay, right? Okay. However, during the test, we accept, right? We accept if you put less or equal, we accept, but we want only this value. Okay. Anyway. Okay. So can you understand about it? This one? Ada apa-apa soalan yang you going to ask? Is it clear to all of you? Okay. Ya, Daniel apa-apa nak tanya? Daniel, Firdaus?
Tak ada, Doktor.
Tak ada.
Just
Okay. The rest? Clear? Oh, Basha, Nur Alia, Afifah. Basha, kenapa Ras? Raise your hand. Tekan Doktor. Okay. Alright. Okay, clear eh? You have any question? No? No?
no, Doktor.
No,
Okay, no, Doktor.
Doktor.
Oh, no. Wah, baru dengar suara. Ada ngantuk je petang-petang ni. So, today we have achieved how to calculate the statistic error and we have achieved how to check whether our system is stable or not. Okay? Betul? Alright? Okay, so I think that's it for our class for today. I will see you again on this Sunday, inshallah. So thank you for your attendance. Alright, and happy holiday, happy weekend on this weekend, inshallah. Alright,
Thank you.
okay.
Thank you, Doctor.
Thank you, Doktor.